We built our entire modern civilization on top of a physical force that most of us cannot actually see and barely understand. If you took a high school physics class, you were likely taught that electricity is a flow of electrons moving through a copper wire, behaving exactly like water flowing through a pipe. But the electrons themselves do not carry the energy from a power plant to the device in your hand. In fact, they barely move at all. What we call electricity is actually the mastery and manipulation of an invisible electromagnetic force. When a switch is flipped, the actual electrical energy travels through the empty space outside the wires. It moves as an electromagnetic field directly from the source to the load. The electrons inside the metal are merely passengers. They are guided by this surrounding field, drifting forward at a fraction of a millimeter per second. They slowly bump into the wire's atomic lattice, releasing their kinetic energy as heat or light. To establish this guiding field, a power source creates a steep gradient of surface charges, an excess of electrons on one end and a deficiency on the other, arranging themselves along the exterior of the entire circuit. These surface charges lock into place almost instantaneously. Because this setup process is limited only by the speed of light, a light bulb turns on the moment you close the switch, regardless of how slow the electrons inside the wire are actually moving. Harnessing these invisible fields, putting energy into the surrounding space, and forcing the electrons to take it out exactly where we want, is the absolute prerequisite to powering a modern society. On an industrial scale, all traditional power plants share one underlying mechanical purpose. They are built to conjure these electromagnetic fields. In 1831, Michael Faraday discovered that moving a magnet in and out of a coil of wire forces the creation of an electric current. Whether a facility burns natural gas, splits uranium atoms, or uses falling wire, the end goal is exactly the same: use kinetic or thermal energy to spin massive magnets inside giant coils of wire. This chart shows the return on investment timeline for two typical power plants over 25 years. A natural gas plant is cheap and fast to build, breaking even around year 7. A nuclear plant generates immense energy, but requires massive upfront borrowing and takes years to construct, pushing profitability out to 16 years. Generating power is an economic calculation. It is a constant challenge to spin these magnets as profitably as possible. Once generated, the next hurdle is pushing these electromagnetic fields across vast distances to where the demand actually is, without losing the energy to electrical resistance. In the late 19th century, two competing systems fought to become the standard infrastructure in what became known as the War of the Currents. Thomas Edison advocated for direct current. His system functioned well for densely packed city blocks, but it suffered severe power loss when transmitted over long distances, requiring a costly power station every square mile. In response, Nikola Tesla developed a competing infrastructure based on alternating current. Alternating current allowed the use of transformers. By stepping up the voltage for transmission, the system proportionally reduced the current. Lower current meant less friction among the electrons, minimizing the energy lost as heat over hundreds of miles of wire. In 1896, engineers harnessed the immense power of Niagara Falls using AC generators. They successfully transmitted massive amounts of electricity to the factories of Buffalo, New York, proving the system could operate across large geographic expanses. Tesla's alternating current became the global standard, weaving a permanent, massive web of high-voltage fields across the planet. In the final mile of the grid, local transformers step those high-voltage fields back down, allowing them to safely enter homes and appliances. For decades, humanity used this energy primarily to burn filaments for light or to spin motors. Then we learned how to use the current to process information. Early telecommunications and computing relied on large, fragile glass vacuum tubes to control the flow of electrons and amplify signals. Engineers eventually discovered they could dictate a precise one-way flow of electrons through solid silicon. This eliminated the need for bulky vacuum tubes and gave birth to the transistor, and eventually the modern microchip. Controlling this exact microscopic flow of electricity is what made modern computing hardware possible. Zooming back out to the macro level, managing this global web requires an extreme balancing act. Electrical supply must precisely match electrical demand in real time, every second of every day. Integrating intermittent renewable energy sources like wind and solar complicates this balance. They remove the constant, reliable baseload that coal and nuclear plants historically provided to the grid. To keep the grid stable, excess power generated during sunny or windy periods must be saved. This requires massive, geological-scale energy storage solutions. Pumped storage hydroelectric projects act as the world's water batteries. When there is excess power in the grid, it is used to pump water up a mountain into a high reservoir. When demand spikes, that massive volume of water is released back down through underground turbines to generate instant electricity. Meanwhile, material scientists are searching for the ultimate efficiency upgrade: room temperature superconductors. If discovered, they would allow electrons to flow without any atomic resistance, eliminating heat loss from transmission entirely. Keeping this system running requires a continuous series of massive engineering feats and precise economic calculations. Our modern existence depends on maintaining this invisible heartbeat.